Hello physicists, and welcome to the first ever episode of Curious Conversations. Today I'm joined by a man who predicted the appearance of 2019's black hole image in his Ph.D. titled Gravitational Lens Effect of Galaxies and Black Holes 33 years before the image was produced. In the 1990s, he went on to develop the groundbreaking Convergent close coupling theory for electron-atom collisions. Into the 21st century, he has continued his work in quantum collision theory and contributed to many significant projects, including the largest scientific experiment on Earth, the International Thermonuclear Experimental Reactor. Since 2010, he has been the head of physics and astronomy at Curtin University. Professor Igor Bray, welcome to the show.
Thank you very much. Delighted to be here.
So, Igor, during that little introduction there, I mentioned Convergent close coupling theory.
Mm-hmm.
That's been a pretty significant achievement for you and your colleagues throughout your careers. However, it didn't always seem that way.
That's true. When we first developed it, we developed it in response to substantial discrepancies between theory and experiment. And that was our motivation for developing the latest and greatest, most accurate approach to the problem. What turned out is that when we finished, we got the same results as other theorists. And so we were particularly disappointed. However, it turned out that in many other areas, the theory was exceedingly accurate, got very good agreement with the experiment where other theories could not. And so we went on to suggest that the initial experiments that were the initial motivation needed to be revisited.
So how confident should theorists and experimentalists be to make a suggestion like that?
Obviously, very, very confident, and you can develop that confidence by comparison much more broader than with a specific experiment. There are hundreds of experiments that require theoretical verification, and by understanding what it is that they're measuring and what it is that you're calculating, you can readily look for self-consistencies. And in the case of atomic hydrogen as target, this is much more difficult to create in a laboratory compared to, say, the lithium, a beam of lithium atoms. But the chemistry of the two are very similar. They're both essentially one electron atoms. And the experiment with lithium, we reproduced incredibly well, the same kind of experiment. And yet that wasn't the case for hydrogen. So we didn't actually say the hydrogen experiment was wrong. We just suggested that it ought to be revisited based on the fact that we had such good agreement with similar situations and similar targets.
And so to do that, you used Convergent close coupling theory, or CCC theory.
Mm-hmm.
So what actually is CCC theory? Does it make any assumptions, or is it an ab initio theory?
It is an ab initio theory, but even with ab initio theory, there are some basic assumptions, such as we believe that the non-relativistic quantum mechanics is sufficient for describing collisions at the energies that we were interested in. So, so these are fourth, fifth order corrections to have relativistic, but that wasn't the issue. The differences with experiment were like factors of 2 and or 50%, something like that. So, so it is an ab initio theory, and it should yield essentially exact results for non-relativistic quantum mechanics.
So what made you so sure that you were right and the experiments needed to be revisited when you developed CCC theory?
Well, those were when we first compared with with that experiment and other calculations. We found that our theoretical results were very similar to other calculations, and therefore disagreed with the experiment. Then application of the theory to similar collision systems where even more accurate data was available, and we know that it was more accurate because the statistics were far better, much smaller error bars, and we reproduced those particular experiments, whereas other theories could not. And so it did two things. It suggested that our original calculations were also correct, and that we developed a theory that was superior to others.
So some people might not have appreciated when you challenged their experiments and when you said my theory is better than all the others. So they might have disagreed with you. They might have disliked you a little bit after that. Despite that, they still went ahead and replicated the experiments.
Yes. So first of all, how you say things matters. And of course, I would not use that kind of language to suggest that they were wrong. It's a scientific argument. It's an argument of ideas. So the fact that the theory works so well on similar experiments and applicable more broadly, that it did really, really well where even other theories could not, and it was understood why, was sufficient motivation. But so there was no personal element in terms of people being unhappy. We have predicted experiment to be less accurate than our calculations, probably around 10 times in my career, and on every occasion we were found to be correct. But one example where some of our German colleagues who did the first measurement of circularly polarized photons doubly ionizing helium, they got a particular result. Our calculations did not agree, but they were very supportive of us to publish our results in one of the highest profile journals called Physical Review Letters. And with their support, that paper was published, and they then used that publication to argue for a lot more money to rebuild the apparatus, ship it to a different light source that was going to be more accurate, and remeasure. And when they came back, they had perfect agreement with our calculations.
So as you said, there was no personal element there.
No.
But there are some people who you would have worked more closely with than others, like Dimitri Fursa, for example, who I recently discovered was your first ever PhD student. Second PhD student. So how important is it to understand the strengths and weaknesses of the people you work closely with?
It is exceedingly important, and in this case we can talk about strengths and greater strengths. Working together, I would say the greatest advantage our group has had over our competitors around the world is that with Dmitry Fursa and also Professor Elisha Kadyrov, we've been together for over 25 years, and we have worked together, and it is so important to be there to look after each other, raise our families together, and we have complementary skills and overlapping skills. So our students can go from one to the other. It is, people talk of having a critical mass in a research group, and that's what this allows. So we've been very successful in attracting external funding for postdocs, and we've always had several postdocs and lots of outstanding PhD students. And you need a group of senior staff to be able to look after that. So working cohesively, supportively together is a critically important part. It's teamwork.
You now work with those people, Dmitry Fursa, Elisha Kadyrov, but it might not have been that way. Because your PhD was in astrophysics. So at Curtin we have the four streams: applied materials, astrophysics, and mathematical physics. You jumped from astrophysics to mathematical physics from your PhD into what you work in now. So is it possible for students at Curtin to do that, and is it encouraged?
Absolutely. So as part of the summer scholarships or research projects, we get our students to engage in the research projects very early on. Many will do so by the end of first year. And we encourage them to sample many of the research projects and do jump across, even if they like a particular area in the first that they try. Of course, we don't force anybody to do so, but we encourage diversity so that by the time a student makes a real commitment to, say, the honours project, which is half of the value of the year, or to then go on to a PhD, which tends to define where the person is going to work in their sort of research activities. I'm the exception in that case. So our students get there being fully informed of the diversity of offerings that we have here at Curtin. My specific story is a very unusual one, and it will take quite some time to explain how it was that I jumped from an astrophysics related focus to quantum collision theory. It's related to changing universities and unexpected opportunities arising, and also includes a secretary in the United States not knowing how to spell Australia.
So should people take advantage of opportunities like what you just mentioned?
Well, yes. So I let students know to be always on the lookout for various opportunities. Life is about being opportunistic. It's very important to have a plan A and work towards that, but always pay attention to what's happening around you. If there are better opportunities come about, certainly for them to be considered. One shouldn't go jumping from one to another and not being stable in any one area. That does not look good on a CV. But when there are major leaps, so like starting a PhD or finishing a PhD and considering becoming a postdoc, those are good opportunities to reevaluate where is the world is at, where are the opportunities, what countries, what's the state of affairs, even the political state of affairs. All of those considerations do come in, and also in terms of partnering. Often by the time students finish PhDs, they may have a partner who also has a career or not, whatever the situation may be. So a lot of communication, a lot of talking to supervisors, fellow students, partners, parents, friends, everything comes into it.
Well, speaking of collaborations, like you've mentioned there, a very significant project going on today that requires the experience of physicists from various disciplines is ITER, the International Thermonuclear Experimental Reactor, which you've had a little involvement in. Upon first plasma expected in December 2025, according to their website, iter.org, ITER will be the largest fusion reactor ever built, but it won't produce electricity. So if we can't harness that energy that ITER produces, then why is it being built? What problems is it going to solve?
Yeah. So ITER is a very expensive $30 billion largest scientific project on the planet. And it's full of robotics and diagnostics because its goal is to produce 10 times more energy than what is put in for about 4 minutes. And if that is achieved, then the next generation of reactors, and they are now being designed, called DEMO, would indeed be generating electricity 24/7. So maybe about 20 years ago, we have built fusion reactors, one called JET, Joint European Toroid, in Culham Laboratories near Oxford, and it reached the break-even point. Having understood all of the physics of that, they realized the size and scale required for a reactor that would be able to generate 10 times more energy than what is put in. And ITER is that experiment. That's why it's called International Thermonuclear Experimental Reactor. Its goal is not for production. So if it works, and we won't know that. First plasma is mid-2020s, but the cycle of fusion generation, which will require deuterium and tritium in the plasma, that would be in the early to mid 2030s. And if that is successful, then the demo reactors will start being built. They are being designed now. I have already been invited to a conference at the International Atomic Energy Agency to discuss the design of demo. Many people are very confident that ITER will work. At the same time, it is experiment, and so many things will go wrong. But ITER is full of diagnostics and robotics that will help us to understand all of the physics that goes on inside. When that is fully understood and it is the turn for demo, then that will be a lot cheaper because you don't need all of those diagnostics and robotics inside because you know what's going on.
So there are certainly a lot of problems being solved there. But outside of fusion, what other problems are there for mathematical physicists of the future to solve?
Well, the mathematical physicists address the biggest problems of, I'm not sure if it's called of humanity, but of the universe. So how did the universe begin? Dark energy, dark matter, all of those issues, the biggest issues, and unification of theories, developing quantum gravity to become consistent with Einstein gravity. All of those issues are being addressed by mathematical physicists. So research opportunities are absolutely enormous in that regard. But there are also many more applied areas that the skills of physicists in general, so mathematical physicists, to my mind, not only have a very strong knowledge of physics, mathematics, but supercomputing as well. And that skill set is broadly applicable in a huge range of areas, more applied areas, like medical physics, for example, or even financial physics. So there are companies, finance companies, that will only employ theoretical and mathematical physicists because of their knowledge of mathematics, problem-solving skills in physics, and, of course, knowledge of computing. So the world is an oyster, will continue to be so for basically physics graduates, experimental physics graduates, theoretical mathematical physics, materials physics, all of those areas will live in a knowledge-based economy, and the physics graduates are highly sought after.
And is that range of applications the reason why Curtin insists, or the Curtin physics degree rather, insists that such a broad range of compulsory units are taken?
Yes. So I described the physics degree at Curtin as having three cultures of world-class mathematics, world-class computing, and world-class physics. That combination is rather unique in the world, and because of that diversity is why we limit choices for students, because they need to have enough of each discipline to be credible within those disciplines. But that particular combination gives our graduates that highly sought after skill set that is required in many diverse careers. So of course it would be irresponsible for us to have a degree that would excessively limit the options of our graduates. And particularly now that as our numbers have picked up, the diversity of students deserve a large diversity of careers where their education will make them succeed.
On the topic of education, despite being employed in a research-only capacity, you've mentioned previously, well, not in this interview previously, but historically, that you always find time to teach. Why is that?
Well, I have always worked with the motto that teaching is the most important thing we do on par with raising our own children. And my own children are now in their 20s, but I of course started, and this became obvious to me soon after they were born, and that is that life is about paying it forward. So when I was young, even younger than now, and my focus was on my own career and making sure that I had a job before raising a family, and that was fine. But once my wife and I had children, we really had personality changes, and that we started really focusing on the younger generation. And that was a natural transition for me as my career progressed in the university sector, is to engage with that younger generation. That's why I do a lot of outreach. I really enjoy engaging with the younger generation, and I feel it is my job now is to help them to succeed in the same way that the older generation helped me succeed.
So you find that to be your responsibility, but how much responsibility would you say then that students have of their education, or other educators and institutions?
Well, of course, it is said it takes a village to raise a child, and a child is part of that village. So all of us have a large contribution to make. You may have heard me say to younger people that at this stage of their lives, their job is to be selfish. I don't mean that in a superficial way. I mean that they do need to focus on themselves. To make a sort of humorous remark, I say you have to solve the one-body problem, right? Don't attempt a two-body problem until you've solved the one-body problem. You need to know who you are, what you want in life. These are things that you have to take charge of, right? Then, when you feel you know what you want, contemplate two-body problems, and certainly don't contemplate three-body problems until the two-body problem is solved. So everybody contributes. Us more senior people are here to help, to discuss, to be a soundboard for our students, but our students must take charge of their lives. Don't wait for somebody else to decide what's best for them. And that means not parents, not even friends or siblings. It's about the student. They have to take real charge of their lives.
That's all the questions we've got for today. So thank you, Igor, for agreeing to be here today.
It is my great delight. Thank you for making the opportunity.
If you want to see more content like this, make sure to hit the subscribe button and ring the little bell icon. Or if you want other people to see our videos, please like, share, and comment below.
And until next time, stay curious.